Will do. Okay, so 4A and 4B, we have been differentiating, we've been finding stationary points, then we learned about defining them, or whether they're maximums or minimums, using our table with the slopes in there. But not all curves are nice ones. Okay, the curves that we've had so far have been nice, like cubics with their lovely bends coming through, or parabolas. But we know there are other types of curves out there, and not everything differentiates nicely. So, let's go through this list. Sometimes curves can have discontinuities. And if there's a discontinuous point, it means that we can't find a derivative at that point. Some of the possibilities when the derivative y dash is undefined at a value x equals a. So this may occur when there is a vertical asymptote, okay, obviously discontinuous point. And it says, suppose also that the function is defined at x equals a, so not just our asymptotes, but there are types of graphs that do exist at x equals a, but we still can't differentiate them. For example, it would be when two sides of your curve meet at an acute or obtuse angle. Or there may be a vertical tangent at that point x equals a, where the gradient has the same sign on both sides, and that curve passes smoothly through the point. Or, last one, there may be a cusp at x equals a, where the curve becomes vertical on both sides of the point, like our absolute value graphs. Remember the cusp, the pointy part. All right, so the ones we're doing today, we're going to have to keep an eye out for those spots where we can't differentiate to see what is happening there. So question 1a, it says differentiate y equals 1 over x bracket x minus 6, find the zeros and discontinuities of y dash, and then use a table of slopes to analyze the slope of the function. Okay, so we can differentiate that curve. First of all, I will have to change the way that it is written to do that. I can't differentiate a fraction when I have x's on the bottom in brackets like that. So I'm going to expand the brackets out. Y equals 1 over x squared take away 6x. And you could do a quotient rule here, but you don't need to because it's a 1 on the top. I'm going to bring that up to be a negative power. So it'll be x squared take away 6x to the power of negative 1. So this is a function of a function differentiation. To do this, quick recap, you bring the power down to the front, so the negative 1 comes down. You multiply by the derivative of the bracket. So I have an x squared minus 6x. The derivative of that is going to be 2x take away 6. Then you multiply that by the original bracket, x squared minus 6x, and subtract 1 from the power, which will become a negative 2. Now, that's a bit of an unusual way to see that. We'd probably want to put that back into a positive power for the final result for that. So I'm going to have negative, and I can even, that first bracket, there's a factor of 2 in there. I could factorize a 2 out to be 2 bracket x minus 3, close bracket. And on the bottom, I have my x squared minus 6x to a positive power of 2 when it's on the bottom of the fraction. Now, I was doing this on a separate step. I can also take the x factor back out of that bottom bracket, but if I take a factor of x out, I have to square it because of the squared sign. So it would become, leave the top, it would become an x squared when I bring it out, x take away 6 in brackets squared. Does that sound familiar with what we were doing with numbers when we were doing our transformations? Now that everything is factorized and in that fraction form, the things that make the top 0, the x values that make the top 0 are going to be my x-intercepts. So I'm going to have 1, 0, or x-intercept at x equals, what makes it 0? 3, excellent. On the bottom, whatever x values make that 0 are going to be my discontinuous points, which would also in this case be vertical asymptotes. Okay, so where are they going to be?
6 and 0.
Yeah, so discontinuous at x equals 0 and x equals 6. Okay, I've found all that information, but the question then says that I need to use a table of slopes to now analyze what's happening with that function. So that's the table that we drew up last lesson with the 3 rows. We have got x's for the first row, our gradient on the second, and slope for the third row. My x values, there are 3 of them, so there's quite a few we need to put in here. The smallest value I have is 0, so space, then 0, space, then 3, space, then 6, and another space on the end. And I need to test points in between. So I'm going to choose -1 for the left of 0, 1 to the right of 0, between 3 and 6 I'll choose 4, and above 6 I'll choose 7. The zeros and discontinuous points, we don't have to sub them in. We already know what's happening there. When x equals 3 is a 0, which means gradient is 0, which means horizontal line. The discontinuous points are asymptotes, which means I need to put stars in, because they don't exist, at 0 and at 6. Let's see what happens in between. So if you sub in -1 into the derivative, so you're subbing into here. You could sub into that one if you like that version, but I'll probably go into there. If you sub in -1, give it a go, what do you get? Sorry, say louder.
8/49.
Yes, good. Okay, subbing in a +1. 4/25. Should I just tell you the other ones? So for 4, it is -1/32, and 7 was -8/49. Remember, it's not the size of the number that matters, but whether it's positive or negative. So 8/49 is positive, so we want to slope that one upwards. 4/25 is also positive, sloping upwards. -1/32, so going down, and another negative on the other side of that as well. So you can see in the middle of that table, we have this increasing, 0, decreasing. There is a maximum turning point. Okay, so we found a maximum point, and we can also tell where the rest of the curve is increasing and decreasing. Let's write it down one thing at a time. So we have a maximum at the point 3. What is the y value of that point?
Sub it in.
Sub it in. To where?
The original.
The original, very good. So I haven't worked that out over here, so we get to this point where I need the y value of that. So I have to sub the 3 back into the original equation, and we should get -1/9. Okay, for the rest of that graph, anywhere to the left of that turning point is always positive gradients. See how it's like a positive gradient, positive gradient? I do have a discontinuous point there, so there is that one spot where there's an asymptote, but it's going to be increasing everything to the left of that turning point. So I'm going to say here that it's increasing when x is less than 3, with the exception of 0, except at 0. The 0 is an asymptote. Okay, and on the other side, what's happening? They're all negative gradients, so they're decreasing for all values of x that are greater than 3, except for what?
6.
except at 6, where that other asymptote got in the way. All right, good. That's part A. Part B. Analyze the sign of the function and its domain. Find and describe any vertical and horizontal asymptotes and then sketch the curve. So this is pretty much the last topic that we did on graphs and equations. Okay? We want to talk about domain. What's the domain of my curve? I've got some asymptotes, right? So it can have any value of x except for those asymptotes that I've found, which were at x equals 0, so x cannot be equal to 0, and x cannot be equal to 6. That's the domain. Then it says to describe the vertical and horizontal asymptotes. All right, so here we go. Vertical asymptotes first. So vertical asymptotes are going to be at, well, we've kind of just done that, haven't we? They're at the x equals 0 and the x equals 6. That's why we were discontinued. That's why my domain was the way it was, right? But I had to write that down because it did specifically say to write the domain. So there it is. But I don't just want to write down where the asymptotes are. I need to kind of analyze it a little bit because we like doing that. Okay, so we're going to see what is happening as x is approaching the 0 from the plus side and x is approaching 0 from the negative side. And we will also have to do as x is approaching 6 from the plus side and as x is approaching 6 from the negative side. To do that, you may want to draw yourself up a little table. I can't use the other one because the other one was a gradient table. Okay, so don't mix up the two tables. The table I would need for this would be an x, y, normal y, and sine that we were doing in the last topic. Okay, so I'm only worried about my two vertical asymptotes, so I can change the values that I've used from last time a little bit. So 0 and 6 are the ones that I need in the middle. They are stars in here because they are asymptotes. And we're just wanting to see what is happening to my y values on either side of that. So let's use -1, 3, and 7. 3 was a bit of a sneaky choice because, remember, 3 was my turning point. I actually already found out that that one was -1/9 when I did the last question. And so that just leaves 2 more that we have to sub in. So if we sub -1 back into the original equation, you will get a +1/7. And into 7, putting 7 in there, you will get a +1/7 there as well. Which means the sign is positive there, negative in the middle, and then positive again. So let's have a look now. As x is approaching 0 from the plus side, what is y approaching? 0 on the plus side, it's negative. Negative what? Infinity. Okay, I mean, I haven't subbed in a value that was particularly close, so my value wasn't very big. Okay, but they're asymptotes, so they're going to be either approaching positive infinity or negative infinity. So if we use that sign, the negative, we know it's going to be going to the negative infinity. Whereas on the negative side, which is the -1, that's a +1/7, which means that y is going to be approaching a positive infinity. If we do the same thing for the 6, on the positive side, y is approaching positive infinity, and on the negative side, it's negative infinity. Is that getting easier to do? Good. All right, so we've analysed our vertical asymptote. We also need to look for our horizontal asymptote. Now, horizontal asymptote, to find it properly, showing the correct working out, we need to take our original equation and divide through the highest power on the denominator. Okay, so my original equation was y equals 1/x² minus 6x. I'm using the expanded version because that makes it easier to divide through by the highest power, which is an x². So if I divide through by x², I get 1 over x squared over x squared is 1 minus 6x over x squared would simplify to be 6 over x. Now, the reason we do that is because if we're trying to find out what is happening as x is approaching infinity or negative infinity, these usually work out to be the same if it's a horizontal asymptote. So usually you can get away with just doing one, but anyway. The fractions, the 1 over x squared and the 6 over x, if you're putting infinity in for those denominators, they become 0. Okay, so that's going to be, what's going to be left, it's going to be, I'll write this down here, or I'm running out of room, it's going to be y is approaching 0 on the top over 1 minus 0, which is equal to 0. And it would be the same for the negative infinity. I'm just going to write it twice. Okay, after all of that, I hope you've got a little bit of space left because we do need a sketch. Okay, so a tiny little sketch in there, got a little corner there still to spare. I want to draw. Most of it is happening to the right of the y-axis. You only need a little bit of space to the left because of the asymptotes, right? So my vertical asymptotes were at 0 and the other one was at 6. So remember to label them. Vertical asymptote at x equals 0. Vertical asymptote at x equals 6. And I have a horizontal asymptote coming across here at y equals 0. I found a turning point. Do you remember where it was? It was at 3.
3 minus 1.
Very good. So 3 right in the middle of those two asymptotes, which makes sense. And minus 1/9, not to scale, I'm going to put that there. Because it's not to scale, I'm going to write that next to it. So 3 minus 1/9. Now, if we use our table of signs and all that analysis that we did over there, when I am on this 0 asymptote, when I am on the negative side of that, I'm at positive infinity up here, so starting up high. When I'm on the other side, it's at negative infinity, so it's going to be way down low. So it's going to be high on this side, low on that side. For the 6 vertical asymptote, it's going to be negative on the negative side and up high on the positive side. So you can see what's going to happen in between already. This is going to connect up like that. And there's the middle part of my curve. The horizontal asymptote, we were told that our curve is approaching this y is equal to 0 line. So these two bits on the side are going to come down and are going to bend around approaching that y equals 0 line. Okay, there's the curve. All right, let's do an absolute value.
That's great.
Question 2.
What? No, I can't do
There is a few questions today. We better keep moving.
No, I can't.
All right, question 2. Question 2. Sketch the absolute value of x plus 2 and x minus 4 in absolute values using transformations. To do that, you want to consider what the graph of x plus 2 and x minus 4 will look like. Just forget about the absolute value signs for a second. That would be a parabola. And we could find the zeros of that parabola. So the zeros would be at x equals negative 2 and x equals a positive 4. To draw it a little bit more accurately, the turning point of that parabola is going to be directly in between the minus 2 and the 4, which is when x equals 1. So when x equals a positive 1, I can find the y value by subbing that back into my equation. Y will equal 1 plus 2 or 1 minus 4. and we will get a negative 9. That's without the absolute value. So I'm going to do a little sketch of that. So negative 2 and positive 4. They're my two x-intercepts, and my y-intercept is at 1, negative 9 down here. Not y-intercept, did I say y-intercept? Turning point. My y-intercept is where? Minus 8. It would be the number when I times the 2 with the minus 4. If I was expanding out those brackets, I would get a negative 8 at the end. Okay, so my y-intercept would be over here at negative 8. This is the graph without absolute values. What do absolute values do? They make everything negative positive, correct. So that means any y values, all the stuff below the x-axis, is going to get reflected up above the x-axis. So these parts out the side that are already positive, they are going to stay the same. Okay, so I'm drawing my final graph in red here. The turning point, which is at 1, negative 9, when it reflects up, it's going to be at a 1, positive 9 up here. And my y-intercept, which was at negative 8 before, will be at a positive 8. And my curve will come down like that. So these lovely little points that have been made here are called? Nope. Said at the beginning of the lesson, starts with C. Cusps. Cusps. Excellent, Ashton. Okay, so they are cusps. At those points, it is very difficult to draw a tangent and try and get a gradient there because it's not doing the right thing. Okay? Sorry? We're looking at it now.
Yes, I actually can't do this. I'm so tired.
You'll just sit there and listen. Part B. So we've drawn the graph. That was the first part. Part B says, hence, find the derivative of y dash. So we need to make a note. Once we've identified that we have those cusps, we need to write down that we know that there is going to be no tangent at x equals minus 2 and x equals 4, where those cusps are. So I need to look at what is happening to the gradient around all those points, okay? So when x is less than minus 2 and also when x is greater than 4, those parts of the curve were already correct when I didn't have the absolute value signs, those parts there. So if I want to find the gradient of those, all I have to do is take my equation without the absolute value signs and I can differentiate that. Okay, I can't differentiate it while it's in brackets, so I expand it out, which is x squared. I'm going to do the middle two terms together. I have a minus 4x plus 2x, so minus 2x minus 8. And then when I differentiate that, y dash equals 2x take away 2. Okay, that equation would be the equation of the gradient for the outside parts of my curve. But when I want to find the gradient when x is between negative 2 and 4, that was the part that got reflected up, and that parabola was the x plus 2, x plus 4, oh sorry, minus 4, there's a minus sign in there, would have been the negative version of that parabola because I've reflected it. And then if I expand and differentiate that, that would be the equation of my derivative at that point. So it's going to be the negative x squared minus 2x minus 8 that I had before. Expand the minus through. And then y dash, my derivative. Please make sure that this stays y when I'm just expanding things. But remember to put your y dash in when you're doing the derivative. So y dash equals negative 2x and plus 2. So that means that I can draw up a table of slopes that will describe the gradient of that curve at the different points, which is what question C here wants me to do. So the table will involve the x values, which is going to show the -2 and the 4, but also remember we found our turning point, so let's put that in there as well. So I'm going to put -2 space, my turning point was at 1 space, and then I had another asymptote at 4. Okay, let's pick some values in between. So -3, 0, 2, 5. At -2 and 4, we have asymptotes, stars. At 1 was my turning point, which means that I have a 0 gradient, which is my flat line. When I sub into my derivative equation, and here you have to be careful because you'll have to change which equation you're subbing into sometimes. So if x is equal to -3, I'm subbing -3, that's less than -2, I'm subbing into that equation. So I'm going to do 2 times -3 is -6, minus another 2 makes -8. Negative slope. If I sub 0 in, 0 is in between these two. So that means I sub into this one, so that's 0 plus 2 is 2, which is a positive slope. And 2 is also still in here. So -2 times 2 is -4 plus 2 is -2, negative slope. And 5 is back in this category, so back up here. 2 times 5 is 10, minus 2 is 8, positive slope. So we have found that there is a maximum. We know, well, we saw that from our diagram, but we've now got it shown in our table as well that there is a maximum turning point at x equals 1 and what was the y value? 9?
Yeah.
However, do you remember talking about global maximums and minimums?
Yes.
Yeah. What would be the global minimum of that graph?
0.
Yeah, 0. So because the lowest point because of the absolute values, the lowest point that they will ever get to is where those cusps are. They are not stationary points like we're used to, but they are the lowest point that curve will ever get to. So we can make a note of that as well. So let's write there are global minima, because that's the plural for minimums, minima, I don't know, sounds Englishy to me. All right, at -2, 0 was the first point, and 4, 0. And we also said there was a local maximum and a local maximum at the point 1, 9. Why is that one only a local maximum, not a global maximum?
Keeps going.
That's right. These ones here would overtake them if we kept going up. It's just a maximum turning point, but it's not the maximum overall. Next page. We might have to continue this on Monday. Question 3. Differentiate y equals x to the 1/3. Find the zeros and discontinuities of y dash and draw up a table of slopes. Okay. If I want to find the zeros and discontinuities, the x to the power of 1/3 is the same as a cubed root of x. Where does that pass through on the graph? You are awake? It does go through the origin, because if x was 0, y would be equal to 0. Is there any discontinuous points? No. Okay, it's just going to change the slope. That's right. So that's something we need to think about from the start, that y is equal to x to the 1/3 graph. It passes through the origin. And is continuous. Okay, so I don't have to worry about finding discontinuous points and analysing all of that stuff. But I do need to find the gradient. So y dash, differentiating fractional powers, still bring the fraction power to the front, a third x, subtract 1 from the power would make negative 2 over 3. Now we like to put our negative powers back on the bottom, so that would be 1 over 3x to the positive 2 over 3. So by putting it back in that form, we could see that that gradient is not going to have any zeros, but it's going to be discontinuous at x equals 0, because x equals 0 would make that denominator 0, wouldn't it? So this means it has no zeros, but is discontinuous.
Can we just say it's continuous?
The gradient is discontinuous, this is talking about.
Does that mean that the gradient is infinite like that?
It's going to be,
Yeah.
we're going to do it with the slopes table. So it says, draw up a table of slopes.
Oh, it's coming off. So what's that?
X, that's all right, they're trying to copy from out there. I've been watching them. So 0. 0 is my discontinuous point for my gradient, okay, which means no value here to be found. But if I sub in something less and something bigger than, if I sub in negative 1 into my gradient, I'm going to get a positive third. If I sub in positive 1, I'm also going to get positive a third. And you'll see that the slope is positive, doing something interesting, and then positive again. It's not an asymptote though. What could it be? What was one of the other conditions that I mentioned at the beginning of the lesson before we ran out of time? Not a cusp, there was a different one.
Horizontal point inflection?
No, vertical. It becomes vertical, yes. Okay, so it says to examine the behaviour in part B. I've done my table of slopes, part B now. Examine the behaviour near y dash near the 0. So I'm going to be looking at the y dash. We're used to doing this into our y equation, but we have to do this with our gradient. So what is happening to y dash as x is approaching 0 on the plus side and as x is approaching 0 on the negative side? Well, what do we find in our table? If I went to the negative side of that 0, it was approaching a positive number. But what do you think that's going to be? What am I going to say y is approaching? Y is approaching infinity. And if I go to the negative side of 0, it is also a positive a third, so it's also going to be approaching positive infinity. So that tells us that there is a vertical tangent. Ooh. At the origin 0, 0. Part C says to examine the behaviour of the derivative and y as x is approaching infinity, as x is approaching negative infinity, and then sketch the curve. So y dash, now we're trying to see horizontally kind of what's happening here. As x is approaching infinity and as x is approaching negative infinity. If I'm putting, where's my y dash equation? Y dash. Okay, so my equation was 1 over 3 x to the power of 2/3. Technically what I should be doing here is I should be going through and dividing through by my highest power on the denominator. Yes. So on the top would be 0 and on the bottom would end up being a 1. So it's going to be approaching 0. Do I need to write that? I need to write that down? No, you're right. Make sure you understand. I don't know, taking a long time, but I'm wanting to make sure it makes sense. Bye, Ashley. Okay, at negative infinity, that becomes a positive again. So it is also going to be approaching 0 there. And that is telling us that the curve flattens. Okay, because if the gradient is approaching 0, it means the gradient is coming up close to a flat line. Not at it. Okay, it was an asymptote, remember. It was not an asymptote, it was a discontinuous point that we couldn't find. But we know that it's going to be approaching a 0 gradient, a flat line. But what happens to y as x is approaching infinity and as x is approaching negative infinity? This is back into the original equation. If I was to put x is equal to infinity into here, what's y approaching? Infinity. If I put negative infinity in there, what's it approaching? Careful. Yes. Okay, let's quickly draw this sketch in. We'll have to do the last question next week. Oh, I'll just record it for you, will I? Okay, so we have a vertical gradient at the origin. We know that the curve is going, as we go out to positive infinity, my curve is going to be quite steep to start with, but is flattening out to a gradient of 0. That's what that flattening out part was. And if I go to the negative infinity, it's starting steep, but it's also going to flatten out to a 0 gradient. I could put other points on there if we wanted to. So if I subbed in x was equal to 1, I would get y is equal to 1, and it would give me another point on the curve. Okay, on to question 4. We want to differentiate y is equal to x to the power of 2/3, find the zeros and discontinuities of y dash, and then draw up a table of slopes. So if I think about the equation y is equal to x to the power of 2/3, I could have any value of x that I wanted into that equation and I would get a y value. So there is actually, because there's no fractions or anything else involved here, there is no discontinuities. And we would also know that if x is equal to 0, then y would be equal to 0. So that gives us that it's going to pass, or it passes through our origin, which is 0, 0. Now if I differentiate that, y dash equals the 2/3 comes down the front, x stays the base, and I subtract 1 from the power. 2/3 take away 1 is negative 1/3. If I put that back on the denominator, I would get 2/3x to the power of a positive third. So again, there's no x's on the top of that fraction, which means that there is no zeros, but the denominator would have a discontinuous point when x was equal to 0, because that would make my whole denominator 0. So it'll be discontinuous at x equals 0. Okay, so then we're asked to draw up a table of slopes. So in our table of slopes, we're testing what is happening around that discontinuous point, which was 0. So we want x equals 0 in the middle. I want to find out what's happening to the gradient, and my third row is going to be the slope. So I'm going to choose -1 and +1 to go on either side of the 0. 0 is discontinuous for the gradient, so stars in there. If you sub in -1 into the gradient, you get -2/3. If you sub in a +1, you get a +2/3. Okay, so it's interesting that the gradient has changed on either side of that discontinuous point. We have got a negative slope there and a positive slope there. What does that mean? Let's have a bit more of an investigation in part B. Examine the behavior of the gradient near x equals 0. Okay, we want to see what's happening a bit more. So y dash, as x is approaching 0 on the plus side and as x is approaching 0 on the negative side. So when I put it into the table before, on the negative side, my y value was negative, which means y is going to be approaching negative infinity. On the positive side of 0, it was a positive 2/3, which means y dash, sorry, these are gradients, is approaching infinity. Okay, so if a gradient is approaching infinity, that means we're getting a very, very pointy part of our graph, a positive infinity and a negative infinity pointing towards each other, which is a cusp. So therefore, there is a cusp at our point 0, 0. Part C, examine the behavior of y dash and y as x approaches infinity and x approaches negative infinity, and then sketch the curve. So we want to see what's happening for our very large values of x. So x approaches infinity, x is approaching negative infinity. For the gradient, if x is approaching infinity, into my gradient up here, if x is approaching infinity, that means my denominator is approaching infinity, and that would be 2 divided infinity, which is basically 0. So my y value, my gradient, is approaching 0. And negative infinity is the same deal, that is also approaching 0. That means, again, if my gradient is approaching 0, that tells you that the curve is flattening or flattens. What is happening to my y values as x is approaching infinity and as x is approaching negative infinity? So into my y equation, which is back up here, if x is approaching infinity, infinity to the power of 2/3 is still going to be infinity. And negative infinity to the power of 2/3 is also a positive infinity. You could check that by subbing in a big number if you needed to. So both of those are approaching positive infinity. So that means that there's no horizontal asymptote there, because they're both getting bigger and bigger and bigger. Okay, so to draw the result of all of this, we have a cusp at 0, 0. We know that the gradient on the positive side of that cusp is going to be very, very large. It's like infinity, very, very large gradient. And as we go out to infinity, it's going to be approaching 0. So it's going to start super, super steep and flattening out slightly. Even though it's not an asymptote, but it is flattening a bit. And on the negative side, if we want to go to the gradient just to the left of 0, my gradient is super steep, but is negatively sloping, and it is also approaching infinity, which means it's flattening out. So it is also going to come up very, very steeply, but negatively, and flattening out, going in that direction. And that's what my graph looks like. We could put an extra point on there. I could sub in x is equal to 1, and if I put that into my original equation, 1 to the power of 2/3 is equal to 1. So I would get a point on there like that. All right, that's it.